In this lesson, we're going to be doing a dynamics example and then using that to practice some of our Matlab skills. The example we want to look at is a ball that is being thrown at some velocity v and some angle theta. And after some time, it's going to be caught at the same height at which it was thrown. So we'll have some thrown height, we'll have some caught height, and really what we're interested in is this range, which is going to be a function of theta. We're going to hold our velocity constant whenever we're doing the analysis, and we're going to be changing theta. So here's what we know. The velocity at time zero has a magnitude which is equal to this constant v. We also know the starting height, so the y position at time zero, that's equal to h, which is also equal to the height at time t1 when this thing is caught. We know that our position in the x direction at time zero is equal to 0. We're going to define that. And then what we're interested in finding is the range as a function of theta. And we're going to set that equal to our Sx at time t1. So here's how all this plays out. We know that with constant gravity, we're going to follow a parabolic trajectory. And we also know that this should be symmetric about the midpoint. So we're going to exploit that symmetry in order to solve our problem. So we're interested not only in this time t is equal to t1, we're interested in this time where t is equal to t1 over 2. All right, so at time 0, we know our position, we know our velocity, and we're going to be feeding our theta into our function, so we'll essentially know that. So we can split at time 0 our velocity into x and y components. So our vx at time 0 is equal to our starting velocity multiplied by cosine of theta. Our Vy is going to be our velocity multiplied by sine of theta. Now we can use this information to find out what's happening at some generic t. For Vx, we don't have any acceleration. So we know that the velocity at time t is going to be equal to our starting velocity. It's never going to change. But our velocity at time y will be changing. It's going to be our starting velocity, this Vy of 0, minus our gravity multiplied by whatever time we're currently at. Since we have no acceleration in the x direction, our position at time t is just going to be equal to our starting velocity, this Vx of 0, which I'm going to write as v cosine theta. That entire quantity just multiplied by whatever time we're currently at. And we can find our position in the y direction as well, but because we're using symmetry, we actually don't need to. Let's look at time t equal to t1 over 2, so this midpoint time. At that point, our Vx is still going to be the same as our starting, so this is still v cosine of theta. And our Sx is going to be equal to our range divided by 2. We know that just from symmetry. The other big thing we know is that our velocity in the y direction at t1 over 2 is equal to 0. So we can rewrite this using our Vy at any time equation and say that this is equal to v times sine of theta minus g multiplied by the time that we're using, which is t1 over 2. So now this is something that we can solve for t1 because we know v, we're going to be varying theta, and we know what g is. So to solve this for t1, we just move this term to the left-hand side and then divide everything over. So this will be t1 is equal to 2v over g times sine of theta. And then once we have this t1, we can plug it into our Sx equation. So Sx at time t1 over 2 is equal to v times cosine theta multiplied by t1 over 2. And this we said was equal to our range of theta over 2. So we can just multiply both sides through by 2 and come up with our range. All right, so now that we have the math done, let's move over to the Matlab side and work on that. So now that we've done the math, we're going to go and move over to Matlab in order to plug in some different values and see what our results are. So starting up Matlab, you'll see a couple things right away. First off, the toolbar has a lot of options in here, and we'll get into some of those. You should see a little box that describes the current folder, which may or may not have some files in it. That defaults to a Matlab folder, which is generated when you install Matlab. That's inside Documents, inside your username. You'll also see a workspace. This contains any variables that you've defined as you've been working. And then the big thing that you should see is the command window. So the command window is where you can put in commands. So here I can use it as a calculator. I can determine what certain variables are named and then use those variables in mathematical commands and so on and so forth. But really what I'm interested in doing is creating a script that I can run over and over again that has multiple commands. So to get rid of everything I've done, I'm going to use the CLC to clear the command window. And I'm going to use the clear all command in order to get rid of anything in my workspace. And what I want to do is I want to create a script that contains a number of commands. So in order to do that, I'll move up to this new script command and go ahead and click that. And once you click the new script command, the editor screen will open up with an untitled script in it. So I'm going to create a comment. The % is the comment in Matlab, and anything following a % is ignored by the interpreter. So I'm going to create a comment that describes what we're trying to do today. And we are trying to find the range of a projectile. Once I have that in, I'll go ahead and save. So I can click the save button up here and give this a name. Now it's important that you do not put any dashes or spaces in your names or Matlab will not be able to run them. So I'm going to name this range of projectile. And once that's saved, I'm going to go ahead and put in those same two commands I used a second ago. First, CLC to get rid of anything that's in the command window, and second, clear all. This semicolon just means that it's the end of the command. It's essentially the same thing as moving down to the next space, but we can actually put multiple commands on a single line this way. I'm also going to use one more command, and that's close all. So this command here gets rid of any windows that are open, which will be important later as we get into plotting. So with that done, I can go and get started on my program. So the formula that we want to put in is r as a function of theta. And we said that this was equal to v times cosine theta multiplied by t1. And we said that t1 was equal to 2 times v times sine of theta divided by g. So these are the two commands that we want to put in. So as I'm writing this program, I'm going to start at the end and actually move backwards. I'm going to start off by writing what we want as our final result, which is this range. So I'm going to call that variable r, and I'm going to set that equal to what we said right here. This v times cosine of theta multiplied by t1. And I can just copy and paste that down here. Now, if I try running this, I can run it, it'll automatically save and try to run, and it gives me an error because we don't know what pretty much any of these things are. We know what cosine is, but we don't know what our velocity is, and we don't know what t1 is. And so it gives us an error message. And if we scroll up, it stops at the very first thing that it finds a problem with, which is I don't know what our velocity is. So we need to assign each of these variables. Well, our velocity, we're just going to give that a value. And the value that we're going to use is 10. And I'm just going to make a comment for myself that this is in units of meters per second. So our range here is going to be in units of meters. And that we're just putting in there so that we don't forget about it later. Then we'll run this again. And we run into the exact same problem, but if we scroll up, now it's having a problem with theta. So again, we're going to go ahead and plug in this value, and I'm going to set it to 45, and this is going to be in units of degrees. So we run again, and we're mad at T1. So we can go ahead and use this formula for T1. We know that formula, we calculated it earlier. So we can go ahead and plug that in. And we're getting pretty close now. I think the last thing is we need to know what our G is. So since we're using meters and seconds, then we know that G is equal to a 9.81. And this, of course, is in meters per second squared. And finally, we can run this, and we end up with an answer. It gets through all the way. So we have a time and we have a range. So now we need to check to see if these things make sense. Well, the first thing that I'm going to check is I'm going to make sure that our sine theta is working the way we want it to. So if I just type in sine of theta down here, I should expect 1 over the square root of 2, which is about 0.7. And what I get is 0.85. Now, the reason for this is that Matlab expects whenever you put in sine, we are giving it the argument in radians. So instead of trying to convert this to radians, I'm going to use the sine d command, which uses the same thing in degrees. So if I type in sine d of theta, then I should get the 0.7071, which is the same thing as 1 divided by the square root of 2. So now looking back at this, you'll notice some orange underline here. And if you check the error message, it says you can terminate this statement with a semicolon to suppress the output. So it's telling me that if I don't want to see what's coming out here, then I can put a semicolon at the end, and we won't print out what T1 is. But I actually want to see those for now. So I'm going to leave T1 and R there. I'm going to run this again, and we're going to see exactly what our time and range are. So our T1 is 1.44 seconds, and our range is 10.19 seconds. So you can go and double check that by hand to make sure that everything's working correctly, but I'm pretty confident with what we have here. So our next step, we really like to look at more than just this theta. V, we're going to keep the same, but our theta value, we're actually going to change that and do a couple of other things with it. So we can change this really easy and get a new value for both T1 and R. I'm actually going to silence the T1 for now and just do R. But we should get a new value just by rerunning this. And Matlab will automatically run through all the equations so that we can get our new range. And we can run that same thing using 60 degrees, and we should get the same answer because both of those are 15 degrees off of 45. Now that's great and all, but I actually want to go one step further. I want to create a plot where we can see the range as our y-axis against theta as our x-axis. So in order to do that, I actually want to use multiple values of theta. So there are a couple commands that we can use for this. One of those commands, we can just put in each value of theta that we're interested in directly. So we can go by 15s, say, and go ahead and grab as many values that we're interested in. And that creates a row array of all the values that we'd want directly. Now, whenever we want to plot, we probably want more than just 5 values or what we could put in manually. So there are some commands that we can use such as linspace, which allow us to do this a bit more automatically. And if we type linspace and then open a parenthesis, then we'll automatically get some help on how to actually use this. So it tells us that it wants an x1 and an x2, and then if we want, we can put in an n. So x1 here is the starting point. I'm going to start at 15, and I'm going to go to 75. And if I put in a second comma, then it'll tell me that I can put in an n. So I'm going to have 100 points in between those. So if I go ahead and press enter, then it'll show me how it splits up those points among the 75. So those are kind of ugly numbers, but that's fine. Not too much worried about that. We're just creating a plot. So that did what we wanted to. So we're going to go ahead and copy that command up into our theta. And this will create a theta ranging from 15 to 75. Now, the beauty of Matlab is that it treats everything as an array, even if we just have a single value. So by creating this array, all the math should basically still work. We'll have to make just a few changes, and I'll explain those. But everything that we've written is still useful, even as we change our theta. So let's go ahead and run this and see what errors we get. So it's telling us that we have an error using the multiplication because the inner matrix dimensions must agree. So in line 10, what's happening is that we have our cosine of theta, which is an array now because theta is an array. So if we wrote cos d of theta, then we would see that that is an array. We also have t1, which since it's been through a theta, t1 is based on theta, t1 is also an array. So both of those are 100 by 1 arrays. And if you know a little bit of linear algebra, you know that you can't just multiply arrays together like that. So we don't even want a vector-vector multiplication. We want just each of these individual values to be multiplied by each other. So the command that we want to use for this is instead of a normal multiplication, anywhere that we're multiplying two arrays together, we actually use a dot multiplication. So by doing this, we should be able to run through and get a value for r. And this value for r is actually 100 different values based on each of these thetas that we gave it. We essentially just ran through this 100 different times for 100 different theta values. Or really, Matlab did it for us. So I don't want to see all those as text anymore. I actually just want to plot the values. So the plot command, if we open it up, takes an array of x values followed by an array of y values. Well, the data that we want on our x-axis is going to be our theta values. And the data that we want on our y-axis is our r values. So doing nothing else, we should be able to just run this and get a plot out. And we see that we're starting right around 15 and we're going all the way to 75. And our maximum range is right at the 45 mark, which is what we expected, and it's a little above 10. Now, this is great if all you want to do is just kind of get a visual representation and you're not using it for anything. But really what we need to do is give this some axes titles and then an overall title. So the way we do that is by using the title command for a start, and this is going to be the range of our projectile. And for our x-axis, x label, that was our theta values. So we can write theta, and this is in degrees. So I'm going to put in the unit as well. And then for our y label, that was our range, and that was in meters. So we need these quotes to tell Matlab that what's in between the quotes is a string. It's a list of characters that it's going to be using. So we can run this now, and we should get not just our plot, but also our labels that we decided on and our title. So we could go deeper into changing around some of this plot. We could create some different lines, like maybe with some different velocities. But we're at a pretty good stopping point, and we have the start of what you need to know to get working on Matlab.